Ironically, men first came to the Antarctic in search of warmth. They came for skins to make coats and for oil to fuel the lamps and lubricate the machines of Europe and North America. The kill was fantastic. In 1 year alone, a single ship took more than 100,000 of these fur seals. At the peak of the boom, there were about 200 ships. In little more than 30 years, several species were butchered to within a hair's breadth of extinction. "70 years later, man returned. By now, man's needs had changed. The rich products of the whale went into soap and cosmetics, candles and margarine, and later into animal feeds and fertilizers. Again, in the name of Northern Hemisphere convenience and profit, whole species were almost wiped out. And again, through ignorance and greed, an industry all but died. In a mere blink of the eye, man had upset an intricate web of life that had been undisturbed for tens of millions of years. It was concern about this that led to the first systematic biology in Antarctica. In the 1920s and 30s, the British, worried by the falling numbers of whales, ran a continuous program of research. It was this work that began to reveal just how bountiful the southern oceans are. It showed how cold, oxygen and nutrient-rich water from Antarctica mixes with warm water from the tropics at the Antarctic convergence, turning it into an explosion of life. The Discovery 2 expeditions were prompted by the falling numbers of the ocean's largest creature, but its findings gave us a new insight into one of the smallest. For near the bottom of the food chain in the southern oceans is the tiny krill. The word is Norwegian. It means tiny fish or whale food. But virtually all the life of the rich waters depends on it. It's the staple diet of millions of birds, seals, whales and fish. This interdependence of one species with another is the basis of much modern biology. The first step is observation. What lives there? What does it look like? What does it do? The next stage is to understand how the species fit into their environments. What is so intriguing about sub-Antarctic biology is that although the water is so cold, life is so profuse and so highly developed. On the harsher Antarctic mainland, life is more primitive. Here, the success of an adaptation lies not in numbers, but in the fact of survival. On the northern limits of the continent, there are fields of moss. In them lives Antarctica's only insect, the mite, a sort of wingless fly. The nearer one gets to the pole, the simpler and more primitive life becomes. Like mosses, lichens and algae appear in widely extreme conditions. In the dry valleys, only a few hundred miles from the pole, it takes a special kind of adaptation to cope with 6 months of darkness, piercingly cold temperatures, and winds so dry that the mosses become freeze-dried. But with the arrival of the sun and meltwater from the glaciers, incredibly, growth restarts within minutes. Even here, on the land, water is the key to life. In some ways more remarkable still is the existence of life in the water under the ice of the dry valley lakes. The lakes are most unusual. For one thing, the water gets warmer as you go down instead of up. For another, because the lakes are enclosed, the water becomes extremely salty from the chemicals in the surrounding rocks. Warwick Vincent is studying how the tiny plants adapt to these very peculiar conditions.
Immediately beneath the ice is a region of fresh water, a region of very cold water. It is some of the clearest and some of the cleanest water to be found anywhere in the world. Beneath that region is a layer of water that is actually salty. And in this layer, the plant life is adapted towards slightly warmer temperatures, slightly greater salinities. The temperature actually increases with increasing depth in this layer. The layer of ice over the lake acts like a pane of glass. At the very bottom of the lake, the water is some of the dirtiest, some of the nastiest to be found anywhere. It is completely devoid of oxygen. What we are doing is to measure the efficiency of plant growth. A question of special interest to me is, how do these cells overwinter? How do the plants survive the full 6 months of total winter darkness with no obvious source of energy to sustain their life throughout that period?
It's a good question, for plants grow by photosynthesis, capturing the energy in light and converting it into growth. It's the fundamental process that distinguishes plants from bacteria. It's basic questions like these that the scientists must have answers to if we're to appreciate the interdependence of life. The point here, for example, is that plants are pre-packaged energy for animals. The higher up the food chain we go, the more questions there are. The mechanisms are more complex, so the ways in which adaptations can be made are more varied. Scientists were surprised to find species of large fish under the ice shelves deep inside the Antarctic Circle. Besides the question of how they manage with no plant food for long periods through the winter, there's the problem of the cold. For under the sea ice, the water is supercooled to about 2 degrees below its normal freezing point. John McDonnell works at the University of Auckland.
If the fish we know at home were put into the freezing waters of the polar seas, they would rapidly cease to operate. On the other hand, polar fishes, Antarctic fishes and Arctic fishes, living under these permanent ice cover, have adaptations which prevent them from freezing and enable them to continue living. These adaptations have been studied for the past 20 years and include such changes as low temperature enzymes and antifreezes in the blood.
The antifreeze ingredient is a natural glycoprotein. It's a compound that stops the seeds of ice from developing into crystals. Here, it's being injected into the bloodstream of a cod from warmer New Zealand waters to see if such an adaptation is interchangeable. And if the word glycoprotein sounds familiar, it is. It's simply nature's version of the antifreeze we put in our cars. This sort of research may seem rather obscure, but there can be practical benefits. Here we could find ways of improving methods of storing blood for hospitals. For the scientists, though, the real value often lies in the knowledge itself, rather than in any practical application. And they will often go into difficult areas on the basis of only qualified guesswork, and with no real certainty of where they'll arrive. Their first step must always be to discover and record, and then to understand.
This year I'm working on the difficult region where the nerve contacts the muscle and activates it, causing it to contract. Because it's such a complex zone, many things can influence it, including temperature. In the Antarctic fishes, I expect to find that there will be a fairly narrow temperature zone in which the nerve transmitter is active, and that outside this zone it will be deactivated by cold and by heat.
To understand adaptations, scientists must make a series of journeys. It's not enough just to look into the intricacies of the body. They must also go into the physical world of the creatures they're studying. Adaptations may be behavioural as well as physical, and we can see this most easily in higher species like the Weddell seal. Of all mammals, the Weddell seal lives the furthest south. For an air-breathing animal, it spends remarkable periods underwater.
The longest dive we've measured by a Weddell seal was 73 minutes. That's out of a sample of about 15,000 dives.
Gerald Koyman of the Scripps Institution of Oceanography has been looking at how Weddells dive.
Centered all right, Jared, like that? Okay, here's the first one. Beautiful. Good. I'm gonna get the... Next time you come forward, make sure it's running forward to that one. Up. Right, right. Okay, here we go. Second one. Yeah, that way on the next one you come back around there. Right. That's good. Yeah.
By attaching depth recorders with radio telemetry, he's found out how deep they go.
Okay, I got the slack on there one.
Oh, no, you can hear it, but it's very weak.
Let's get it back off. You ready?
And since the radio signal alters when the device is submerged, he can tell how long the dive is.
Okay. Ready?
All seals have up to twice as much blood by volume as land animals, and its hemoglobin content is much more concentrated, so they carry more oxygen. The body chemistry is different, but that's only part of the explanation.
When Weddell seals dive, they anticipate the length of the dive they're going to make. And if they're making a long dive, the blood is restricted to the heart, the brain, and the lung. And in this way, on the longer dives, they conserve the oxygen stores in the blood for the essential organs.
Amazingly, the seal seems to be able to think ahead and then alter its body functions to cope with the conditions it's about to face. This isn't unique. All vertebrates can do it. But what is unusual is how exaggerated it is in seals. We don't yet know how they anticipate the length of a dive or how they control the mechanism. In zoology, it's often difficult to separate physiological from behavioural adaptations. The work, though, is fascinating. Weddels, like most seals, spend most of the year scattered about searching for food. In late November, early December, they collect together on the ice, and this is when mating occurs. But gestation takes only 10 months. If it started straight away, the pups will be born in the following winter. So the fertilized egg doesn't start developing for 2 or 3 months, ensuring birth in summer. The newborn pups are better adapted to the land than to the sea in which they'll live. They have very little fat, and it's fat which is the insulator from cold water. But the fur they're born with is excellent protection from the freezing winds. They put on the fat incredibly quickly. In 1 week, their birth weight doubles. By 6 weeks, when they'll be weaned, it will have gone up 5 times. After a few days, the pups begin to enter the water. This is the time when the holes through the ice become as important as the food they lead to, so the holes mustn't be allowed to freeze over. If they do, it puts pressure on the remaining holes, and this affects the social structure of the colony. It's often difficult to interpret behavioural displays, for they can serve a variety of purposes.
Seals appear to make about 35 different calls underwater. When we analyze them, it appears that there are properties within those calls that could be useful for echolocation or sonar. We do know that some of these calls are used in important social contexts. Females use them for protecting their pups. Males use them for displays at territorial boundaries and for defending those territories.
Now we see the seal with fascination and with awe. But when man first saw it, there was no magic, simply murder. Today, this is what we're coming for: krill. Only about 2 inches or 5 centimeters long, Euphausia superba is the largest of the Antarctic species. But delicate as it is, it's estimated to be the world's largest single source of natural protein. For man, with hungry mouths to feed, it's just too good a chance to miss. This ship's harvest, though, is knowledge. The scientists want to find out what naturally controls the total population of krill. Already, commercial trawlers are taking more than 125,000 tons each year. World fish stocks are dwindling, and there are growing restrictions on access to traditional fishing grounds. Several nations are investing a lot of effort and money in developing economic ways to catch and use krill. There seems to be plenty to go around. One estimate is 150 million tons each year, but everything that lives in the rich southern oceans depends on krill. It's at the bottom of the food chain. If we make the mistake of overfishing krill, we'll be attacking not just one species, but the whole life of the southern oceans. The reason there's so much krill today is because we butchered the whales. It's hard to get accurate figures, but we think the whaling reduced total numbers by as much as 2/3, and this in spite of an international convention to regulate the industry. In 1982, a new convention came into force, covering the entire living resources of the southern oceans. Will it be any more effective than the whaling regulations? Or will it too be ignored by those who find it profitable or necessary to do so? Perhaps we have learned something. Perhaps this time we won't so abuse the waters of life.